In this section, we'll talk about architecture basics, meaning the basics of computer architectures, and with DevSecOps in mind, helping learners, connect foundational computing concepts, so CPU, memory, storage, networks, to the security and DevOps practices that make up DevSecOps. The goal isn't to make you, hardware engineers, but to give you enough context to understand where vulnerabilities can occur and how architectural choices can influence DevSecOps strategies. We'll talk about what is computer architecture. At its core, computer architecture describes how components of a system, its CPU, memory, storage, I/O, and networks are designed and how they interact. In modern systems, architecture extends beyond a single machine to distributed systems, containers, cloud environments, and virtualized resources. DevSecOps architecture sets out the playing field where automation, security, and operations can be integrated and can occur better. There's certainly a number of considerations, execution stack and security implications around CPU and processing power. We'll discuss memory and storage layers, I/O and networking, and application and OS layers. So, architecture matters in DevSecOps. If you think about performance versus security trade-offs, architectural choices such as encryption, resource isolation can affect speed and safety. Automation alignment is important, where to apply CI/CD tools. Infrastructure as code, observability will depend on how systems are architected. The attack surfaces that are available in the architecture present a potential attack concern or surface. DevSecOps architects should redesign and design architecture with defense and depth in mind. And compliance by design architecture can influence auditability, log collection, data sovereignty, for example. So architecture is the foundation of any modern IT system. It includes conceptual design and the combination of software and hardware that interacts to create a computer system or a platform. Whether in the cloud, on premises, or hybrid, every environment depends on the sound architecture to function effectively. At its core, any architecture must perform at least fetching information or data, decoding it into a usable state, and then executing some command. For example, when you pull up a contact list on a phone, the system fetches the data, associates additional information, and then executes the call. Architectures can be understood across three categories: system design, instruction set architectures, microarchitecture, which is the detailed design of features and operations once the hardware and firmware are established. Architecting for DevSecOps goes beyond simply assembling a set of tools into a tool chain. It requires designing end-to-end flows that embed security, automation, and compliance into the architecture itself, which means aligning system design, software practices, and operational processes so the development, security, and operations function as a unified, resilient ecosystem rather than isolated silos connected by tools. As a way to help explain architecture, we're going to talk about three different types of historical architecture models for systems. In this diagram, we're showing the von Neumann architecture, which is a pretty well-known structure. The idea is there's a single memory space that holds instructions, code, as well as data. So the CPU fetches both from the same bus. And the implications for DevSecOps, there's a code injection risk. Since code and data share the same memory, malicious actors could exploit this by injecting data that gets executed as code. Example, buffer overflows, shellcode attacks, and things like that. You can also have malware and ransomware thriving in von Neumann systems because executable and data boundaries are blurred. Mitigation strategies for DevSecOps can include enforcing strong memory protections and secure coding and dynamic static code analysis in pipelines. Second architecture approach is something called the Harvard architecture. In this case, there are separate memories and buses for instructions and data, common embedded systems, digital signal processors, and Microcontrollers use the structure typically. There's implications for DevSecOps, reduced attack surfaces compared to the von Neumann structure. Since instructions and data are physically separated, it's harder for attackers to inject malicious data as code. It's also more predictable that the deterministic execution can help with security critical real-time systems and automotive and medical device applications, for example, because the code is accessed consistently and accurately and with the same timings without being interrupted by data accesses. There are challenges. Updates and patching may be more constrained in embedded Harvard systems. Attackers may pivot to firmware tampering or supply chain compromises instead of runtime injections. There are mitigation strategies, so strong firmware signing, secure OTA update pipelines, one-time access pipelines, incorporate software bill of materials for embedded systems into those pipelines, and continuous monitoring of device integrity at attestation checks, for example. So the third type of architecture we're talking about here is a mixture of Harvard and von Neumann. Many modern CPUs, ARMs, x86s with caches and so on use a hybrid approach where instructions and data may have separate caches, but they access a unified memory. There's a lot of implications for DevSecOps here. Performance versus security trade-offs. You're providing efficiency and speed, but also reintroduces potential von Neumann style vulnerabilities such as speculative executive attacks like meltdowns, Spectre attacks. You have broader attack vectors, the side channel attacks, cache timing attacks, and speculative executive flaws can become real risks. There are mitigation strategies here as well, incorporating microcode and firmware patching into CI/CD and release governance, include hardware-aware security testing in DevSecOps pipelines, use runtime monitoring and anomaly detection to catch exploits. Bottom line of these three types of architectures, the von Neumann is flexible but higher risk of injection type attacks. Harvard is more secure with separation, but introduces challenges in patching and updates. And the mixed architecture is a practical compromise, but introduces complex side channel vulnerabilities requiring vigilant patch and monitoring processes. A common consideration when you're talking about microservices and DevOps is different approaches of using monolithic architectures or microservice architectures or service-oriented architectures. There's a lot of key differences that you should be aware of that are relevant for DevSecOps. The application structure and complexity, for example, a monolith is really a single unified code base with a single deployment unit, simple to build and test initially, but grows complex and harder to secure as it grows and scales. Whereas microservices, the application is decomposed into independent, loosely coupled services, where each service can be developed, deployed, and scaled independently, but introduces more moving parts effectively to assemble an entire service. The implication for DevSecOps and monolith security testing and compliance checks can be centralized, but become slow and heavy. Whereas with microservices, DevSecOps must scale automation and governance across the multiple services without creating bottlenecks. So the complexity of pipelines can increase. It's the trade-off for the speed. Also, if you think about attack surfaces and vulnerabilities, a monolith provides a single deployment artifact, which is smaller external attack surface, but if compromised, the attacker could gain broad access across the entire system. Whereas with microservices, a large attack surface due to many APIs and network services can occur through the APIs, and vulnerabilities can be isolated to one service, but east-west traffic, service-to-service communication introduces newer risks. There's some implications here. Microservices demand API security, service mesh controls, zero trust policies, and DevSecOps pipelines must scan dependencies, container images, Kubernetes manifestos continuously. If you think about the difference from a point of view of deployment in CI/CD, Monoliths, there are fewer deployments. It's easier pipeline governance, but harder to scale with agility. Whereas microservices, you get frequent deployments for many services. It requires highly automated CI/CD with built-in security gates. The implications for DevSecOps and microservices: DevSecOps must ensure consistent policies across distributed pipelines, often with infrastructure as code and policy as code tools. Another consideration is monitoring and independent response. With monoliths, centralized logging and monitoring is easier to aggregate but harder to isolate issues. With microservices, distributed logging and telemetry requires observability platforms, tracing, metrics, logs, and security monitoring must correlate events across many services. The implications for DevSecOps is microservices demand advanced observability and anomaly detection, often using AI and machine learning to connect dots across services. Another final consideration here is governance and compliance. The monolith is easier to enforce compliance because there's one pipeline with one release artifact, whereas microservices, it's harder to maintain compliance across distributed services, each with potentially owned by different teams. The implications for DevSecOps: organizations must adopt standardized security frameworks, policy as code, compliance as code to ensure services don't drift. Bottom line is monoliths have lower operational complexity, but a single vulnerability can compromise the whole system. Whereas in DevSecOps, it's simpler but less agile. Microservices have greater flexibility and resilience, but have a larger attack surface and higher operational burden. DevSecOps must emphasize automation, observability, and zero trust to keep pace.